Thank you, Jing. Whenever I see Jing, it's mostly we talk about food, which are the best restaurants to go to and so forth. So it's a great pleasure to be here. And I mean, if you think my experiments are difficult, I just talked to Harry Tom here, and his experiments are insanely difficult compared to what I'll be telling you. So the title of my talk today is the use of the scanning tunnel microscope to perform excitations, maybe lower, because to perform the to perform spectroscopy of various excitations at the nanoscale. And I'd like to go back a little bit on the history of inelastic electron tunneling effect. And this slide here shows the Eva Ever performing the tunneling spectroscopy composed of the metal oxide metal tunnel junction. So here's the bell jar in which he fabricated the sample. And the experiment, in principle, is pretty straightforward in that if you apply a voltage across this heterojunction here, you get the current to flow even though there is a tunneling barrier. And so this is kind of an IV spectroscopy in which it can be used to detect, in this case, the superconducting gap. Okay, so I guess I have to decide which screen to point to. So I guess either way, yeah. So this is the primary result of his measurement in that he records the current versus the bias across this tunnel junction. And at different temperatures, he observed that at room temperature, the IV curve is linear. And as he cooled down to 1.6 K, he gets this curved spectrum here, IV curve here, in which he can deduce the energy gap for this aluminum. This would be aluminum oxide lead tunnel junction. So the conditions here is such that the aluminum is normal, and then the lead is superconducting, and there is a IV characteristic which shows the gap in the lead metal. And so if you divide take the derivative of these curves, dIdV of the superconducting sample in which of the superconductor, that is the dIdV of the data at 1.6 K, over the dIdV in normal, which is the 300 K, you see that there is this characteristic feature that we come to understand as a property of the superconductor, where the gap is in the order of 1.5 millivolt. And so this was the to make sure that what he's observing is due to the superconducting property. He then increased the magnetic field, and at the field greater than 2,400 Gauss, then he sees the suppression of the superconductivity. So the main point here is that this uses the tunneling effect to observe the superconducting gap. And the next example I show you is in this slide here is the invention of the Squid, which happens about the same time, in the year 1964 at the Ford Dearborn Research Lab. At that time, Ford companies doing one of the top places where solid-state physics research and theory have been carried out. And the Squid is actually invented at the Ford company by these 5 researchers, Lamb, Zimmerman, Silver, Jack Levick, and Mersrow. And the reason I like to point this out, you show this slide here, besides the pointing out that Ford company, besides Bell Labs and GE and the other industrial companies, at that time they're still doing fundamental research, unlike present days. And the Squid is actually invented at Ford. There are these two gentlemen, Lamb and Jaklevic, who went on to use the metal oxide metal tunnel junction to see vibrations of molecules inside this junction. In this paper published in 1966, that in this aluminum oxide lead tunnel junction, the same that was used to measure the superconducting gap, that this is the background spectrum. This is plotting now the second derivative of I dV square versus the voltage across the tunnel junction. So in this geometry here, he purposely then put some molecules in the junction. That is, at the interface between metal and metal oxide, aluminum oxide, you evaporate some molecules onto the surface, and then you deposit the other metal contact. And you see that there are extra features which are observed, and these extra features are attributed to the various vibrational modes of the molecule trapped in this tunnel barrier, the tunnel junction. And if you put different molecule in this tunnel barrier, then the spectrum changes. And these spectral features are due to the CH stretch and the bending modes, and then the impurities which are present in this junction are due to the presence of hydroxide, OH molecules on the surface. So in those days, the people tend to publish short papers, but very significant papers, and in this case, just less than 2 pages long. Okay, so this is a first instance where the tunnel junction, the configuration has been used to record the vibrational spectra of molecules. And so in this electron tunnel junction, in the case of the measurement of the superconducting gap and the molecular vibrational spectra consists from the metal oxide metal tunnel junction, where you have the metal and then the tunnel barrier, usually about 20 to 30 angstroms thick, and then the other counter electrode, metallic, another metal on the other side of the oxide. Now this leads then to the scanning tunnel microscope. The scanning tunnel microscope is also a tunnel barrier, but instead of the oxide, it has a vacuum. Okay, so you have a metal and then vacuum that is a gap, physical gap between two metal leads. Okay, so in this situation here, similar to the oxide tunnel barrier, one would expect also to see tunneling phenomena in this particular geometry. So this was actually the motivation for the two scientists. Actually, there are 4 people involved, but most of the time, Binnick and Roro were pointed out as the inventor of this scanning tunnel microscope. The purpose of their experiment was actually just to see whether tunneling occurs through a vacuum gap. And this is the STM geometry schematically. And so it's very similar to the metal oxide metal tunnel junction. In the STM, you have a metal, vacuum, metal, and the electrons can then tunnel across this vacuum gap here. So the main difference between this and the metal oxide metal tunnel junction is that this gap has to be with some technique. You have to maintain that gap to be a well-defined gap. In the metal oxide metal, the gap is determined by the thickness of the oxide that you deposit in your fabrication of the metal oxide metal tunnel junction. So this gap here is about 6 angstroms in the scanning tunnel microscope, and the trick then is to maintain that gap to very high accuracy for the scanning tunnel microscope. Okay, so the purpose then is to measure the tunneling through this vacuum gap. And this is their initial data now published in 1982, plotting on the log scale the current versus the gap. That is the distance between the tip and the sample. In this case, is how much the tip has moved above the sample. So the main result is that since this is a semi-log plot and you get a linear curve here, that means that the tunneling current, the current that you measure, falls exponentially as a function of the distance. That is the gap separation between the sample and the tip. Okay, so this is direct confirmation that you are seeing a tunneling phenomena, because tunneling, the amount of probability for electron to tunnel across the gap, across the vacuum, should depend exponentially on the distance between the two metallic leads. Okay, so the STM, when it was invented in 1982, is mostly for, they would take, it's used for to form images of the samples that you have. So for example, in this case, if you have the tip here and the sample, and then you have, say, impurities or adsorbate on the surface, when the current, when the tip scans across the surface, you will see bumps if you, in this mode, the constant current mode, in that if you hold the current constant in this loop here, then there's a feedback circuit that adjusts the height such that the current is maintained at a constant value. So this is so-called the constant current mode. And in this case, then you measure the separation between the tip and the sample. And so as you go through the corrugations on the sample and then also the impurities on the sample, you then see these height of the tip above the surface vary according to what you have on the sample. Okay, so you get these topographic images. And this is the first data that was obtained for the sample that the IBM group was able to obtain with their scanning tunneling microscope. And this so-called the relief map for the silicon 1117 by 7 surface, each one of these bumps correspond to an atom on the surface. And this first data was actually composites of line scans and recorded with the strip chart recorder, which is kind of interesting. And they were able to see the monoatomic step and 2 atom steps and even the triple atom steps here. And so their sensitivity is, the spatial resolution of the microscope is definitely demonstrated in this experiment. So these are the 2 gentlemen who invented this new technique called the scanning tunneling microscope, and this is their first result. And now you can do much better, with a computer. And this is the silicon 1117 by 7 surface. Each one of these atoms are present on the surface, and these features here are atoms on the surface, and they correspond also to the first relief map that was obtained by Binnick and Rohrer. And so you can, in particular, you see this diamond-shaped unit cell here, which is the diamond unit cell shown here. Okay, now to contrast this technique to the diffraction experiments, you can obtain diffraction, that is using low-energy electrons to backscatter from the surface, and you can record the intensity of the electron that hit the screen as they backscatter from the surface, and you see these patterns here. In principle, if you do an inversion, this diffraction is in the Fourier space. If you go to the real space, then in principle you'll be able to see the atoms on the surface. But the STM is an instrument that allows you to see the atoms in real space. And so the difference between these two are very apparent here, in that one can just visualize the surface atom positions with a scanning tunneling microscope in the real space, whereas diffraction experiments, either with low-energy electrons or X-ray diffraction, the result, the data in the reciprocal space, and you have to do fancy inversions to deduce the actual positions of the atoms of your sample. Okay, so the STM can, in addition to see the atoms on the surface, can be used to image individual atoms and molecules, and these are some of the examples. But if I ask you what these are, these images represent, it will be very difficult to pin down, what these features actually, what atoms or molecules these images represent. And so this is actually a single hydrogen atom on the surface, a single molecular oxygen, the pi star orbital of the molecular oxygen, the acetylene molecule C2H2, and you see these two hydrogen atoms. These bright features correspond to the two hydrogen atoms, and then there's another molecule, the iron with two CO molecules, and these are the two CO molecules attached to the iron atom, which is the sort of the reddish background here. Okay, so one of the since the invention of the STM, one of the goals is to make the STM into a more chemically sensitive technique. So in the metal oxide metal tunnel junction, Jack Levick and Lamb back in 1966 at Ford Motor Company have already shown that in these macroscopic tunnel junctions, you can measure the I, how the current varies as a function of voltage across this gap. And if there are molecules adsorbed at the interface, then from the second derivative spectroscopy, d squared I dv squared, then you can get a vibrational spectrum of these molecules at the interface. Now the problem here is that these molecules are actually physically sandwiched inside this tunnel junction. And there are, to get a spectrum, you'll need about 10 to the 11 molecules in order to get enough signal to have a vibrational spectrum. And the other is that because these molecules are sandwiched in this tunnel junction here, their orientations, how they are adsorbed, how their structures are difficult to determine, and because they are being covered inside this in this interface. Okay, so with the STM, in principle, you are able to detect the vibrational spectrum from a single molecule, and the adsorption structure will be much more easier to determine. It's possible to determine the structure because it is freely adsorbed on the surface. But the geometry is the same in that you have a metal and then a tunnel barrier and then another metal on the other side. You measure how the current varies as a function of the voltage. You vary the voltage, and then you do modulation spectroscopy. You modulate the voltage, and you look at with the lock-in detection, the various harmonics. That is, the second harmonic signal from the lock-in detection give you d squared I dv squared. Okay, so the way that it works is that you measure the current versus the voltage, and then in the another representation of what's happening here is that the tip has electrons occupying up to the Fermi level, and then on the other side, which is the sample, and then the electrons also occupies up to the Fermi level. So you have a bias between the tip and the sample, which effectively change the relative positions of these two Fermi levels. That is, the voltage here would displace these two Fermi levels by E times the voltage that you apply between the tip and the sample. So basically, this voltage here gives you the energy of the electrons that is tunneling through from this vacuum barrier here. Now, most of the electrons tunnel elastically. That is, they go through this junction without losing any energy. About 1% to 5% of the electrons can tunnel inelastically if the bias or the electron energy is sufficient to excite that particular whatever excitation that is present inside this molecule. And so one of the excitations is the vibrational excitation. That is, if the bias is sufficient to excite this vibrational mode, then in the second derivative, d squared I dv squared, you'll see a peak at the bias that corresponds to the vibrational energy. Okay, so this type of spectroscopy, it can reach about 0.6 MeV or 5 wave numbers if the temperature is about 600 millikelvin. Okay, so some of the results I'll show you will need this kind of resolution. Now, this inelastic event, as I have mentioned, can correspond to different excitations in the system. So these different excitations can be vibrational motions in a single molecule, or rotation, the molecule can rotate, or the spin. If you have an unpaired electron in the molecule, then you can detect the spin in the single molecule, and then you can detect phonons in the sample. Okay, so this is the first demonstration of inelastic electron tunneling spectroscopy with the STM. And the experiment was done on 3 different isotopes of acetylene, which is C2H2. Now, STM topography basically reflects the electronic structure of the molecule. So the electronic structure of these different isotopes are essentially the same. Therefore, from the topography, you cannot tell which isotope you have for these 3 different features in your image. Now, if you can do vibrational spectroscopy, then you can park your tip on this molecule here, and then do a second derivative d squared I dv squared versus bias. You see that there's a peak at 358 millivolt, which corresponds to the CH stretch of this molecule. And then if you park over here, you see that the vibrational peak here is downshifted to 266 millivolt, which corresponds to the CD stretch due to the isotope effect in between these 2 molecules. And then if you park your tip over this molecule, you see that there are 2 peaks, which reflect the fact that this isotope here has 1 CH bond and 1 CD bond, and there are 2 peaks. So this type of spectroscopy with the STM, vibrational spectroscopy with the STM, can reach the limit of vibrational spectroscopy in that it can detect the vibration of a single bond in a single molecule. And you can do imaging in that you can park your bias at one of these peaks here. Let's say this one here at 358, or at any of the features you have. And with that fixed voltage, you can then scan your surface looking at the, basically give you the intensity at that particular energy. And if you have 2 isotopes here, like C2H2 and C2D2, if you park at the CH stretch intensity, then you see that the CH intensity is over here, which reflect the fact this molecule here, this feature here, is C2H2. If you change your bias to CD stretch, then this area of your image will light up, because that's where the CD intensity is. So that's how imaging is done. Yeah.
Is the mass change enough to explain the shift that's actually changing?
Yeah. So mostly the deuterium and hydrogen, the carbon is heavy enough that the mass of the hydrogen compared to the deuterium is almost square root of 2. That's what it says. Yeah. Mm-hmm. Yeah. Mm-hmm.
How close is it to the gas? You just measure
Yeah. The gas is downshifted. Yeah. So the acetylene in the gas phase, the vibrational peak is about 390, close to 400 millivolt. And this molecule, when it's absorbed on the surface, the electronic structure changed. So the carbon goes from is actually, instead of sp, it goes to sp2 hybridization. So it has it goes more or less to the acetylene goes to CC triple bond. It actually goes to CC double bond. So the CH stretch is downshifted, from that of the acetylene molecule, because the molecule is absorbed on the surface. Okay, so you can actually detect the vibration of a single hydrogen atom on the surface. Here we see the image of a single hydrogen atom, and this then gives a feature at 70 millivolt, which corresponds to the single hydrogen atom bouncing up and down on the surface. In this case, the copper 100 surface. And to make sure that this feature here is vibrational, it's due to a vibrational excitation, then you do the isotope, which then shifts this peak down to 51, which is almost square root 2 downshift in the vibrational energy. Okay, so I'd like to give you three examples of how this technique of inelastic electron tunneling can be applied. First, I'll show you how it can be used to measure the skeletal structure of molecules and the nature of intermolecular bonds. And the second example I'll give you is how it measures the spin magnetic properties of single molecules, and then see how one can deduce the spin vibrational coupling in single molecules. And then the last example I'll show you is how to be able to see the vibrations, single molecule vibrations in the time domain and get some dynamics out by combining femtosecond laser with the STM. Okay, so first I'll show how inelastic electron tunneling spectroscopy can give rise to a new probe, which we call the inelastic tunneling probe, IT probe. And with this probe, one can see the molecular structure, the skeletal structure of molecules, and understand the nature of the chemical bonds. Okay, so to do this, we pick up a CO molecule from the surface. That is, we adsorb CO molecule first on the surface, and then by appropriate conditions or tunneling conditions, we can pick this CO molecule up onto the tip. Okay, so with this CO molecule on the tip, we can measure this mode here, which is the Hinder translational mode, where the carbon and oxygen move parallel in the same direction, parallel to the surface. And this mode here is the lowest energy mode for a CO molecule on the tip. It's about 2.5 millivolt, which is about 20 wave numbers, 2.5 millivolt energy. And then we can use this CO tip to probe the potential energy, to probe the potential of this molecule, which then gives rise to a potential energy of the system of the CO plus the molecule. So what it does is that this CO molecule senses the potential associated with another molecule on the surface. Imagine that you have this molecule here. It has these different atoms and then all these electrons that exist in this molecule. It's going to set up an inhomogeneous potential spatial distribution. And what the CO tip allows you to do is that we can monitor the intensity of this vibrational mode as a function of position at as we scan across this molecule. Okay, so what we find is that this vibrational energy shifts both in position and also changes in intensity. For example, if we this is the lower right-hand corner of this molecule here. And so if we put the tip at different positions, for example, position 1, we see a spectrum here, which with this vibrational energy is at 1.7 millivolt. Okay. If we move the tip to inside this ring here, position 2, you see that the vibrational energy has shifted up to 3.2 millivolt from 1.7 millivolt. If we go to the background here, away from the molecule, we see that it is at 2.5 millivolt times 3 and then times 2 here. Okay, so there's this large shift, relatively large shift in the vibrational energy of a CO because it's sensing different potentials inside this molecule. The way it works is the following. You have this CO molecule, which is attached to the tip. This CO then is in to an approximation, a harmonic oscillator in this potential energy curve here. So the curvature then gives rise to the vibrational energy. So you have this CO molecule, which is at 2.5 millivolt, this vibration here. The carbon and oxygen moves back and forth, and that corresponds to 2.5 millivolt energy when it is away from the molecule, like here, right here. Now, this molecule here has a potential that's going to be up and down like this, something like that, right? So you have a potential, some part of potential is going to have a hump like this, some part will have a trough here. If the CO molecule is over this hump here, basically the CO molecule is feeling both the potential due to the tip and also from the molecule, such that this negative curvature is going to change the potential that the CO is in into a more a less curved potential energy surface. Therefore, the CO vibration is going to downshift. Okay, so whenever the CO molecule is over a potential of the that is scanning over, it has a hump. Then its vibrational energy of the CO is going to downshift. Okay. Now, if it's in the trough region of the potential, then the overall potential that the CO molecule experiences because of this trough here is going to add, make this curvature much steeper here, and therefore the vibrational energy is going to upshift. Okay. And so, so this is the reason why, you know, when the tip is over, the CO molecule is over the position 1 here, it is sensing a hump because that's where the electron density is, because due to the carbon-carbon bond. Therefore, this region here is going to downshift as indicated here. If it's inside the ring, it's seeing an attractive potential, that is the trough here, and therefore the vibration energy is going to upshift to 3.2 compared to the background. Okay, so imaging then is you pick a voltage. For example, you pick the voltage at this dot dashed line here, and then you scan the surface to measure the intensity at each different positions across this area that you are scanning. So if the tip is over the, because the energy that you pick here is going to be high whenever there's a bond, like position 1. And then whenever it's over the inside the ring, it's going to be dark because the peak of the vibration is at 3.2, and you're imaging at 1.7 millivolt here. Therefore, it's going to be dark inside here, but bright along the bonds here. Okay. So this is what you see. So this is the molecule here, the cobalt-thiocyane, and this is the image monitoring the CO translation, this vibrational energy intensity at 1.7 millivolt. And you see that the bright features that you see, bright features in this image correspond to all the bonds in this molecule, and every atom in this molecule can be imaged. So there are 57 atoms and 68 bonds, and if you count, you can locate every atom in this image here. And even you can also image these bright features here that correspond to the lone pair of electrons attached to these nitrogen atoms in these 4 positions here. And those are the lone pair of electrons attached to the nitrogen atom. So if you zoom in this region here, you see and then with higher number of pixels in the imaging, you see that this lone pair of electron can interact with the CH bond in this, the adjacent CH bond, and forming a hydrogen bond inside this molecule here. So these curved features here are due to the interaction of hydrogen at this position with the lone pair electrons. So this lone pair electron can interact with 2 CH bonds, and you can see these features here.
Is there any reason to choose hinder translation mode?
Yeah. So the hinder translation mode is very soft, right? In that it's very low energy. So these low energy modes are very sensitive to the variation in the potential. And so if you use higher vibrational energy, higher energy modes, then the contrast is not there. Yeah. So because it's very sensitive to the variations if you use very soft modes. Yeah. 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 How wide is the molecule? Oh, the molecule. This molecule here is about 10, 15 angstroms.
So
yeah.
How much do you trust the lateral measurement, though? Like if I want to measure the width of a bond.
Oh, this one here?
No, just a single
Oh, single bond, double bonds, and all that. Yeah. Because these are all hybrid resonating. Yeah, so they are all the same bond order. Yeah, so that would not be a good case, good molecule to do that. Yeah, but the other people, other instances where you have a distinct double bond and single bond, you can tell the difference. Yeah, and I think there's an example here. So this is the example of this molecule here, which has a single bond and double bond difference between the single bond and double bond. Yeah. So you can image various molecules like this one here we just shown, cobalt-thiocyanine. This is azulene, which has a 7-member ring and 5-member ring here. And then this is another molecule. And then this is yet another one with a benzene type of ring with a carbon-bromine bonds. So you can image these. And then there are these additional features that you see here, this ring here, which is not in the textbook picture that you usually draw. This is the, because this, see what the technique does is imaging the variation in the potential energy surface. And so the potential energy surface has these features here, ring here, because of the bromine sets up an electrostatic potential away from the bonds. And so these see these images here. And this is ethylene molecule with a C2 and the 4 hydrogens. Okay, so but I think the technique is more, I mean, these are textbook structures. You know, you can verify that, you know, chemists have been correct all along in drawing these schematic diagrams of skeletal structures of molecules. But I think this technique, the contribution of this technique, I think is in understanding the intermolecular interactions. For example, when we think of van der Waals interactions, we usually think about fluctuations in the charges, and these instantaneous fluctuations lead to instantaneous dipole moments, which then interact, right? So we like to study, you know, what is the nature of these van der Waals interactions, you know, whether one can use this technique to say something more about the nature of the van der Waals forces. So we put xenon atoms on the surface. And if you zoom in, you can see individual xenon atoms forming a nice hexagonal pattern on the surface. And then if you zoom in further, you see these features here. These circles here are individual xenon atoms. So this doesn't tell you anything. This is a topographic image. It doesn't tell you anything about what is the nature of the interaction between the xenon atoms that leads to this self-assembly into this order structure. So in using the IT probe, you can actually see lines joining the atoms. So these weak features here. And then I put these dots to designate the position, the center of the xenon atoms. So even in van der Waals interactions, you know, there's going to be a perturbation in the in space of the electrostatic potential that gives rise to these features that connects the xenon atoms. It's very similar to the covalent bonds between carbon and carbon. You draw a line between the carbon and carbon. But what we are saying here is that even for van der Waals interaction, there is a slight electron transfer between into the region between the two xenon atoms, even for van der Waals interactions. The contrast is weak because the amount of electron transfer, that is the electrostatic inhomogeneity in the electrostatic potential, is less for xenon-xenon compared to a covalent bond like between carbon atoms or between carbon and hydrogen, and that's why, you know, the feature contrast is weaker. But the fact that there are still lines here indicate that van der Waals interaction between xenon atoms, there is an electron transfer, even though smaller compared to covalent bond, that there's electron transfer into the region between the atoms, and that's usually how we attribute chemical bonds to, due to the electron sharing of electrons between two atoms. I'd like to show you another example of how this technique can shed new lights into the intermolecular bonds in forming self-assembled monolayers. You know, when you have molecules deposited on the surface, they often form these very nice order structures on the surface. And this is the case for the hexafluorobenzene. And it's kind of surprising that they self-assemble because the fluorine atoms, being very electronegative, they tend to be negative charge. So why do negative charge molecule want to attract each other and form these order structures on the surface? So if you zoom in this area here, we see that they do form a very nice pattern of hexagonal pattern again. Each one of this is this molecule here. And, but from topography, you cannot tell, you know, what is the nature, what are the intermolecular interactions that leads to this self-assembly. And so if we zoom in this area, we can use ID probe to see all these lines that is in between the molecules. So we have this benzene ring. So if you take this molecule here, and then the 6 carbon-fluorine bonds. And then there are other extra features which are designated by these dashed red lines here. And these are the reason why these molecules attract each other to form a self-assembled model layer. These are, if you make a bigger picture of that, you see that all these red dashed lines here, which correspond to these triangular features, and then the lines between them, all these features here, dashed lines, correspond to intermolecular interactions. That is the interaction between halogen atoms that leads to this self-assembly.
What's making the contrast?
Pardon me?
What's making the contrast? Is there an intermediate or is it all current, just tons of current?
This one here is actually looking at the intensity of the CO vibration. It's actually second derivative. Second derivative.
Second derivative of this mode?
Yes, yeah, so the second derivative signal corresponds to this mode of the CO. And so this CO intensity is varying because of the potential landscape of the so whatever the
Can you tell which way it's moving?
the CO, yeah, the CO is parallel to the surface.
But is it along X or Y?
On the tip, it's degenerate. Yeah, the resolution is not good enough to pick out that difference. Yeah, so it's just parallel to the surface. Yeah, so if you have a CO attached to a single atom, the two directions are degenerate. Yeah, XY vibrations are degenerate.
Does the substrate play any role in sampling?
It's actually not. Yeah. So you can do a calculation of the potential energy surface without the substrate. You get the result. Yeah. So because STM is only looking at the very top surface, and so whatever is happening down there, maybe there's some, but it's not seeing it. And if you do a calculation without the substrate, you get the same potential energy surface, the features. Yeah. So yeah. This is a 110 surface. Yeah, so the symmetry of the substrate is very different than the hexagonal symmetry too. Yeah. So it's
Does that explain the helicity? Or it seems like
yeah. The helicity is due to the electrostatic repulsion between the molecules. So it's rotated a little bit. Yeah, and that's due to the electrostatic repulsion between that's the electrostatic. But most of the reason why these molecules bind to each other is actually due to van der Waals. If you don't include the van der Waals in your DFT calculation, you don't get binding. Yeah, about 80%, 90% of the binding is due to van der Waals interactions. Yeah.
Even for these weak, like very weak features that you see,
Yeah.
there's no feedback. I mean, the motion of the carbon, the tip, it doesn't affect.
Yeah, no, it does. Yeah. So the bright features here tells you the potential energy surface that has a hump. Yeah, hump only. Yeah, because we choose that energy. If you choose another energy, you emphasize inside the valleys, which are basically the negative image of this. Yeah. So it depends on what the energy. We purposely choose to take an image at a reduced vibrational energy. The reduced vibrational energy senses the potential energy surface that has a negative curvature. So those are negative curvature correspond where the electron densities are. And so the electron densities correspond to where the bonds are supposed to be. Yeah. So the So the bright features are correspond to the bonds, the lines that we usually draw in these chemical structures.
But the charge on the oxygen doesn't mess up the underlying.
Yeah, yeah. So they actually, when the CO is scanning over the molecule, it actually tilts. It tilts, yeah. It tilts the most at the, on one side of the bond, it tilts one way. On the other side of the bond, it tilts the other way. And that we sense by the vibration energy, because we cannot measure the tilting of the CO. Yeah, so we measure the change in the intensity of the CO molecule vibration. Yeah. Yeah.
So during the measurement, you park your tip at the energy of the
Yes.
CO mode, right?
Yes.
So but then the contrast basically tells you how far you're away from this peak, right?
Yeah, but we fix the energy. So we measure either below the peak or up above the peak.
Which side it goes?
Right, right.
Either goes up or below.
Right, right. So here we pick below the peak, because below the peak corresponds to a downshift in the vibration. Because the vibrational energy is going to shift around. Depends on where you are.
So how do you know it's not going above the peak?
Or it'll go above the peak. It'll go above the peak inside the ring. In all the areas that's dark, it'll brighten up. It'll show up if you go above the peak, because the region dark areas correspond to upshift in the vibrational energy. So if you choose a voltage that's higher than the higher, then you will image these dark areas.
So the shift is always small, that you don't have the scenario that it downshift, but then you go to the other side of your peak. Let's say if your peak is like 3 millivolts,
Right.
park at 1.5.
Right.
Let's say if this downshift a lot, let's say goes to 0.5, then you probably also see a dark.
Yeah. If it goes all the way down, but it doesn't do that. Yeah. It doesn't do that. Yeah.
Either positive slope or negative slope of the peak.
Right. Effectively, that you can do that. Yeah. But the slope is harder to image in real time. Yeah. So we just pick an energy, and then that energy, if you pick an energy, right, and the peak at different positions can be anywhere, right? Can be higher or lower, or Yeah.
So can I have a related question? So the voltage you fix, is it a constant voltage or you?
Constant, yeah. During this image is constant, and then you do a small modulation.
That would be the slope, right? You could do a delta V measurement that would sit and measure the slope.
Yeah, so that one there is just give you the second harmonic. Yeah. So the modulation is to allow you to do modulation spectroscopy. You just shake the wiggle of the voltage. Yeah, we pick 311 hertz. Yeah.
How much is that?
Oh, that one there we modulate about 1 millivolt. Yeah, in this case. Yeah. Mm-hmm. Yeah. So that determines the resolution also of your spectroscopy. Yeah. Mm. Yeah, 1 millivolt depends on what you're looking at. Vibrational, we modulate about 1 millivolt. Spin, I'll tell you, it'll modulate at 200 microvolts. Yeah. Okay, so I'll go to the next topic. Okay. So this is to look at magnetism, single molecule magnetism. And in particular, we find that you have this interesting result that the spin can couple to molecular vibrations, and give you a new type of excitation where the molecular vibrations are addressed by the spin excitation. Okay, so instead of picking up a CO on the tip, we pick up a magnetic molecule, which has a spin. Therefore, you have a spin tip. And the molecule that I'll show you today is nickelocene, in which there's a nickel atom sandwiched between these two flat rings of 5 carbon ring. Now, we can show that it is a spin by doing spin inelastic electron tunneling. So in this Nicolocene here, it has 2 ampere electrons. So it has a spin 1 system. So in the spin 1 system, there are the M states are 0 or plus minus 1 as an M state. Okay, now there is a molecular axis along the molecule, and the spin 1 can have 3 components of the M values. And now the interesting thing here, there's something called the magnetic anisotropy, in that this molecular axis, if this M equals 0, there's the easy and the hard axis. Along the axis here, if the spin align along the axis, then it has a different energy than when it's perpendicular to the molecular axis. Okay, so this gives rise to the so-called magnetic anisotropy energy. You can do a calculation to show where the spin densities of this molecule. So the blue corresponds to an increase in the spin. So there are spin in these rings here. Even though the nickel is the magnetic atom, there's a transfer of spin to the 5-member ring away from the center here. So on the tip, you can do a calculation of this molecule on the tip here. You can see that there are still spin that is at the end of this molecule. Okay, now the magnetic anisotropy energy corresponds to the ground state in this system is S equal to 1, the spin 1 system, and M equals 0. M equals 0 corresponds to the spin with the moment parallel inside this perpendicular to the molecular axis. That's the ground state. And then when the spin is parallel to the molecular axis, then that corresponds to 1, 1, 1, minus 1. So in the absence of magnetic field, M equals 1 and M equals minus 1 are degenerate. Okay, so either the spin pointing up or pointing down, it's the same energy in the absence of magnetic field. Now if you apply a magnetic field, then the 1 minus 1, these 2 states split to give you the Zeeman splitting in the presence of a magnetic field. So we can do various excitations. If there's a magnetic anisotropy, the ground state is the 1, 0, and there is the tunneling electron can excite the spin from the perpendicular to the molecular axis to parallel to the molecular axis. So that corresponds to this excitation here. If you have a magnetic field, then you'll see this single peak split into 2 due to the Zeeman splitting. Okay, so this is a series of spectra here, just to show you that we can detect the spin of this single molecule. The magnetic field is applied perpendicular to the surface, and at 0 Tesla, you see this peak here, and then in the negative bias, you see a dip. That's the inelastic tunneling spectrum. And so this peak here is about 3 to 4 millivolt, 3.8 millivolt. And as you increase the magnetic field from 0 to 2, 4, 6, 8 Tesla, you see that this peak split into 2 peaks here. And from that, you can get the Zeeman splitting or the G value of the G factor of this magnetic molecule. And if you pick out the molecule on the tip, you see similarly the Zeeman splitting of this. At 0 Tesla, you have the magnetic anisotropy correspond to flipping this magnetic moment from perpendicular to the molecular axis to parallel to the molecular axis. The ground state, the moment is parallel, is perpendicular to the molecular axis. So that excitation gives this peak here, which is about 3.94 millivolt. As you apply the magnetic field, you see up to 8 Tesla here, you see that peak splits. And if you plot the position of these peaks versus the magnetic field, you see these straight lines. From the slope, you get a G factor for the single molecular magnet. The molecule, when you pick up on the tip, can have different orientations. Unlike the molecule on the surface, which is always with the plane parallel, that is molecular axis perpendicular. On the tip, depends on how you pick it up, it can have different angles, and that is reflected in the different G factors for the different orientations. Okay, so you can then correspond to this, the magnetic anisotropy peak, and then which split. Okay, now the interesting thing is that if you have two, a molecule on the tip probing another molecule on the surface, then these two spins, which are in this case both a spin of one can interact with each other. You can set up a Hamiltonian, and which in this case, in the presence of a magnetic field, you have three terms: Zeman, Zeeman term, and then the magnetic anisotropy term, and then there is the exchange interaction between these two molecules. So the exchange interaction is the J, and then S1 dot S2. Okay, now you have a triplet state for each one of these. So that means that you can determine using this Hamiltonian the eigenvalues of these of this two-spin system, and it'll be a 9×9 matrix. And from that, you can obtain the eigenvalues. In the absence of magnetic field at B equals 0, you have 9 states: 1, 2, 3, 4, 5. Let's see, 1, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, in the presence of magnetic field, you have 9 states: 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 states from this diagonalizing the 9×9 matrix. And so what do you see then? You can have a different with the electron tunneling, you can obtain the excitation to determine the J, the spin-spin interaction, exchange interaction, and also the magnetic anisotropy, and this state here, excitation from here to here, this corresponds to what we call the double loss. That is a new state due to the fact that when you have two spin systems, you actually have to treat it as one system, that they interact, and you create this new mode at this energy here correspond to, you can imagine exciting the magnetic anisotropy in one molecule, and then another excitation of the other molecule. But it's not a sequential event in that this energy for this double excitation is lower than the sum of the individual excitations, because these two spins are coupled to each other. So the nice thing about this system here is that you can vary the distance between these two molecules continuously and see how the exchange interaction varies as a function of distance. So when far away, that means that at some distance, you see that this is the magnetic anisotropy term, which when the tip gets closer, that is when the two molecules get closer to each other, you see that this single peak starts to split, and this splitting is the J, the exchange interaction between the two spin systems here. And this distance variation is about 0.8 Ångstróm, and you can determine how much it shifts over this distance. So this J term is these two peaks are due to the excitation from the ground state to this value here, and the ground state to this value here. And the difference in here, the splitting here, is this difference in these two peaks here. Now this upper state is forbidden because this corresponds to flipping both spins from either both down to up, which electron cannot conserve angular momentum if you electron cannot flip both spins in the tunneling process if it goes from down to up or up to down for both molecules. Therefore, this is forbidden. And the other interesting prediction from the theoretical calculation is that this mode here, which is the double loss, that is the double excitation of these two molecules, it is independent of the magnetic field, because the overall angular momentum is 0 because for these two states here. So therefore, it would not split like this case here. It would not exhibit Zeeman splitting.
So dipole is also.
Yeah, this one here. Yeah, it doesn't. If you measure as much distance, it doesn't follow dipolar. 1 over r cubed. Yeah, it doesn't exactly. Yeah. So there needs to be some more theory calculation, because these two modes are really coupled. These two molecules are really coupled together, and the energies are due to the couple mode, and the fact that they couple to each other, and that their molecular vibrations. I'll show you that there's a vibrational spin coupling also that you can see.
Do you have data of splitting as a function of magnetic field?
Yes, yeah, I'll show you, yeah. So this is a splitting as a function of magnetic field from 0 to 8 Tesla in 2 Tesla steps here. So we predict that this mode here, the excitation for ground state to this highest energy mode, this peak here, is independent of the magnetic field. And that's why you see from 0 to 8 Tesla. Now this peak here, the J, at some if you pick a separation between the two molecules such that you see the splitting here, you see that as a function of magnetic field, you see more features here. And then if you zoom in this area here, as shown in this panel here, without this peak, big peak here, because it makes the observation of these weaker features more difficult. If you just zoom in between these two big peaks, you see that as a function of magnetic field, this peak here starts to split into 2, and then basically merge to, the middle 2 merge together. So you actually see 4 peaks at some magnetic field region, and that's due to the fact that you have Zeeman splitting for each one of these features here. So you see the 4 peaks here are due to correspond to excitation for ground state to each one of these levels, to this one here, to this one here, to this one here. So you see 4 peaks. Yeah.
Now, why I ask is quantitatively, the exchange coupling J
Yes.
itself has to depend on the electronic levels of the two molecules. And
Right.
the electronic levels of the two molecules are moving with the magnetic field, so that J is not essentially well defined.
Yeah, that might be a higher order. Yeah, that might be a higher order. Yeah, we have to look at these results are 2 months old, so our understanding is still we are still at the point of trying to understand. But I thought that because of the interest in magnetism on this campus, I'll show these results. Yeah. But the data are actually very, very, very exciting. Yeah, especially the vibrational spin coupling, and I'll show you that. Okay, so this is the a bare tip probing the single spin on the molecule, the single spin molecule. So this is a function of magnetic field. We see that this magnetic anisotropy peak split into 2, as we have seen, Zeeman splitting. You can look at the vibrational modes. Notice the higher bias. These correspond to different vibrational modes, vibrations of the molecule. Now, in the 0 Tesla, you see these modes. In the 4.5, you see this broadening, but in the 9 Tesla, you see that these peaks here, this one here, split into 2. This one here split into 2, and this one, these 2 peaks here, each one split into 2, but the middle 2 overlaps to give you this central feature here. Okay, so somehow the vibration mode of the molecule, they split under the influence of the magnetic field, if you apply a magnetic field. So this indicates that there's some kind of spin vibrational coupling which give rise to this magnetic field dependence. Okay, so the crunch comes when we study these 3 different systems here. You have the molecule on the surface, a molecule on the tip, and the molecule on molecule in this two molecule system.
What vibration mode is it?
Yeah. So these are the ring different vibration. We are trying to my colleague Ruchen Wu is calculating this right now. Yeah. But these are the low energy, you know, some of them correspond to the ring going like this, and some of them the rings going like that. Yeah. And so it's different type of modes. Yeah, low energy mode of the ring moving relative to the central atom. Yeah. And so that would be that would be Ruchen Wu's job is to calculate these. Yeah. And so if you look at this molecule here, these three different situations, like this one here, you see these modes. Molecule on the tip, you see these modes. But the interesting thing on the molecule here, you see all these modes are shifted up relative to the. So the purple are the marks of this combined system. The blue these segments, the blue lines here correspond to this case here. So if you have two molecules like this, remember that for the two molecules, you have this double loss mode, the double magnetic anisotropy. You have a magnetic anisotropy here on this excitation on this molecule. There's a magnetic anisotropy excitation on this molecule. And this combined vibrational this magnetic anisotropy excitation occurs at about 7 millivolt. In this case, the magnetic anisotropy is about 4 millivolt. Okay, so what we measure here is not the vibration energy of a bare vibration. That is, you know, without magnetic anisotropy, without spin, these vibrational mode will be downshifted by the magnetic anisotropy, which is downshifted by about 3 to 4 millivolt. Because we know that we cannot measure the bare vibrational energy because the spins are there. The spin in the molecule coupled to the vibrational modes, therefore it's already coupled mode you have. You cannot take out the spin. Okay? But we can have two molecular systems. We can add an extra spin excitation into the system. And relative to these red curves and blue curves, this purple curve, they are shifted up by about 3 millivolt compared to the red and the blue curve. So what that means is that the spin is coupled to the vibrational motions, such that you have a new type of mode which involves the spin and the vibration coupled together to correspond to addressed vibration. That is, the vibration energies are normalized. Okay. So one thing that is another evidence of this spin vibration coupling comes from the magnetic field dependence. So for these three systems here, we have 0 Tesla, 9 Tesla, and these are the and the interesting case again is in this one here, magnetic anisotropy of this combined system, which do not depend on the magnetic field. There's no dependence. Therefore, in the 0 Tesla and 9 Tesla, it doesn't split, unlike these two cases here. So this is another indication that the spin is coupled, in this case, to this double loss spin excitation that corresponds to the excitation of the magnetic anisotropy in both of these molecules. Okay, I'll wrap up, yeah. So the last few words on the time domain, which this is how to look at vibrations in the time domain. Okay, so this is the process we're looking at is that the molecule undergoes this conformational change. We can monitor this. So the question is, what is the dynamics? Okay, so we couple the femtosecond laser to the STM, and then split the pulse into two, and then look at the dynamics of this single molecule as a function of the delay between the two pulses. So this is the two pulses shining into the STM junction, and then we're looking at the rate of this conformational change as a function of delay between the two pulses. So what we see is that if the laser is on, then you have much more flipping events, the transition between these two conformations, and then for a dimer, it's even more, but let's focus on the monomer. Compared to the without light, the transition rate is very low. Okay, so here is plotting the transition rate versus delay between the two pulses. We see that there are these oscillations in the rate, which if you zoom in into 0 to 2 picosecond, you see that there are these oscillations. Okay, so if you do a Fourier transform, you see a frequency at 6.9 terahertz, and then the weak one at 2.7 terahertz. So this terahertz corresponds to a vibration mode of 28.5 millivolt, which decay in about 1.3 picoseconds. And the mechanism of this is very similar to what Harry Tom has done a long time ago doing this coherent phonon excitations in semiconductors. And here we show that similar stimulated Raman process can excite a coherent superposition of the V equals 0 and V equals 1, and this V equals 1 population oscillates in time, and this coherent excitation can drive this conformational change coherently. Okay, so the last slide shows the various people who have done the work on the results that I presented to you on the femtosecond laser coupled to the 9K STM, and then the 600 millikelvin 9 Tesla magnetic field STM in ultra high vacuum. And all the results that we have obtained, there's a close collaboration with my colleague Ruchan Wu, who does DFT calculations on vibrations and spin systems. Thank you.